So surprisingly or not, a lot of our users don't use our all-in-one solution. Some, especially academic labs, some government labs, they have their own peak picking algorithms, or they use vendor peak picking algorithms. For example, Agilent's Profinder is very good for peak picking. It has some pretty sophisticated algorithms and is quite fast. So you might use a vendor or open source such as MZMine or XCMS. There's a lot out there, and peak picking is very challenging. And so if you have an optimal peak picking algorithm, I'd love to hear from you because we're always looking to advance our peak picking algorithms that we integrate with FluoroMatch. So if you have your own peak picking algorithm, which can also include annotation, grouping, and other pieces of evidence that are compiled into one data sheet, you may want to keep that. It could even be using other software that already annotate PFAS, and then you want to use our software on top of that and see what we add of value there. It's a great workflow to integrate as much solutions as possible. In this case, you want FluoroMatch Modular. A little bit more challenging than FluoroMatch Flow, but if you follow closely this tutorial, you should be able to succeed in applying it. So, the first thing we need is we need to download a few things. So we'll need to download ProteoWizard, and that's something you're going to need to convert your files. You'll also obviously want to do your own peak picking, so we'll leave that up to you because this assumes that you have your own peak picking algorithms. And you want to follow any of the tutorials in installing FluoroMatch Flow. They'll also talk about migrating your libraries that come with FluoroMatch Flow to your local libraries. So you want to do that as well. So look at that first tutorial for FluoroMatch 3.0. Now, your inputs are going to look something like this. So if we go into FluoroMatch Modular, there's some example data you can test this on. And so we have a feature table. Again, this is that you create. This is your last step in whatever workflow you have. And name it so that it ends in _neg and make sure it's a CSV file. And then we have our converted MSMS and full scan data. So we'll go to that later, but let's start with our CSV table. FluoroMatch Modular was made to take many different table formats, but it does require a few things for the software to work. First is a row ID. So this is just any number that's unique per row, so there can't be duplicates of the same number, that just signifies that feature. If you don't have a row ID, you can insert and type row ID and go 1, 2, 3, and if you have Excel, you can just highlight those, double click this far right bottom corner, and it will fill in a bunch of numbers. They'll all be unique in order, and that's all you need. Make sure the row ID is spelled like this for the visualizer to work. The code can work with any name here, but the visualizer will be looking for this specific name. Same thing for mass to charge and retention time. These can be in any column. Any column that could have been in D, E, or F. But they should be spelled like this, so replace the names of row space retention space time and row space M over Z. And they both should contain numbers. Mass to charge and retention time is in minutes. If your retention time is in seconds, then just divide it by 60. Create a new column and scroll down to get minutes. And then you can copy and paste this over, paste special, and delete this. Also notice that if your mass to charge is actually just a neutral mass, then we need to change that. So for example, Agilent Profinder generates a neutral mass. And so what we want to do is we want to then, for PFAS, we want to take the mass of hydrogen and subtract it to get M-H, and add the mass of an electron for M-H minus. Generally, most of our ADDX are M-H for PFAS, so that will work quite well. but it is an assumption because there are other adducts we might be looking for in negative mode other than N-H. But it should work for most of these rows and is necessary if you don't know what the adduct is. If you know what the adduct is and you know what the neutral mass is, make sure to calculate the correct mass to charge. And if you can export just a simple mass to charge, not a neutral mass, that's ideal. Most software will just export the mass to charge, and so you won't have to do anything here. And if they export in minutes, you won't have to do anything here. Just rename these. The last thing, that can be it. That's all. And then you can close this file unless you have statistics. So the last thing is if you have statistics, then you might have a bunch of columns with your peak areas or peak heights or concentrations, whatever it may be. And the name of each column might be the name of your sample, for example. But you might want to either rename or make sure that your files, before you run whatever your workflow are named accordingly so that whatever groupings are part of the name. So for example, here's a project done by John Bowden from University of Florida on leachate versus foam. And so you can see every sample that belongs to leachate, which is garbage juice, has leachate underscore in the name. And every sample belonging to foam, which is foamed leachate, which ends up concentrating PFAS. Very interesting work. You should look into it. You can copy and paste that name there and use that for each sample. You put the way that FluoroMatch automatically does statistics. If you look at FluoroMatch, there's an example files, a grouping file, is you have this grouping file. So you put leachate underscore in one row and foam underscore in the other. If you have multiple groupings, you can put more than 2 groupings here. We need at least 2 groupings for statistics to work and at least 3 samples per grouping. Now that you're done with your CSV and you've renamed your grouping file, you can close that. The last step is that we now need to convert our files. MSMS files, such as data-dependent or targeted MSMS, data-dependent, or iterative exclusion, should be uploaded or put in the same folder as your CSV and named accordingly. So DDMS2 for anything that's data-dependent or any MSMS files, and an underscore neg in the case of PFAS where we only have negative mode library so far, and MS2. So in order to do this, go to proteowizard.sourceforge.io again, /download, agree to the license agreements, download it, and then open up the latest version. And then you'll have a number of parameters. So, for example, for Agilent, we're going to do vendor peak picking, 2 is our first parameters. And then we want a threshold peak filter. But before I do this, I'll just show you that in the modular, you have a manual, and that manual has the conversion parameters for thermo and Agilent, and we've also run it for waters if you have any questions in SciEx. So here we have for Agilent the parameters. So you're going to upload the .d files. It's a 32-bit conversion and deselect zlib compression. So let's go over here. 32-bit, use zlib compression is off. We want it .ms2. And then we're going to add all of the parameters just as it is here. You can change those a little. Generally, it won't error, although that could be a point of error. So we have peak picking. Subset number of data points, 2 is necessary so that you don't get MSMS scans just with a single data point. That will cause an error. And then output.ms2. So that's all. So let's just add one more thing then, which is the subset number of scans or number of data points, 2 add that. We might also want to add thresholding, for example, if you want to make sure that we're just not looking at peaks that are not above any intensity that matters. So we can say absolute intensity, most intense, 30 for Agilent, for example. I don't want to look at anything under 30. Make sure that it's the right order. So default array length should always be last, and vendor peak picking should always be first. And then once you browse, put your .d MSMS files here and click start. And then you can click the output directory, should be the same file with your feature table, and export those there. The other thing you're going to want to export is your MZXML files. You can have a threshold here. You do not need this default array. Generally, you just need peak picking. If you want to add some thresholding, that will make the software work a lot faster. And then you're going to change this to MZXML and click Start. And then put those files in the same directory as well. So this is for your full scan data for anything you want EIC visualizations of. Note that in this folder for the MZXMLs, you either want blank or target in the names for things that are going to have EICs. There's also a parameter to turn on and off, whether you want everything to show EICs when you're visualizing it, which can slow down the software, or you just want EICs generated for the targeted and the blank files. So that's it. You should have .ms2 files and with an underscore neg.ms2 and ddms2 in the name, and some underscore neg.csv file at the very minimum in this, and ideally some MZXML files with target and blank in the name. Now you want them all in one folder, and now we can run FluoroMatch Modular. So to run FluoroMatch Modular, go into FluoroMatch Modular, double click the code. You can either open with whatever you have. You can do a text editor. I like EditPad Lite is free. Notepad's another one. You don't want to open it in Word where it might change some of the words and things automatically or change formatting. You could do Visual Studio Code, RStudio, whatever you want. So we've opened it in RStudio already. And note, we're not going to run it from RStudio because unless you link it to the correct version of R, it won't work. So before you run R, you want to make sure you set up your libraries correctly, which means that you want to check your .lib paths. We go over this in the installation tutorial, so the first tutorial in FluoroMatch 3 videos. So make sure to look there and make sure how to set up your libraries correctly for R. Once you're done setting up your libraries, you can press Control A here and C to copy. Now we're going to go into FluoroMatch 3, Flow, R 4.2.1, bin, X64, Rgui. Note, we'll put this directory in the comment section of the video so you can look at it and follow it there. So we're going to double click that Rgui to make sure that we're using the right version of R that also has the right version of packages installed. And then we're going to highlight, control, and run this here. Now, you should see that all the packages installed correctly. If I scroll up here, this is all the package section is mostly the beginning. And you'll see some warnings about them being built for 4.2.2, even though it's 4.2.1. That's totally fine. So on and so forth. And so once it gets to the error box and nothing errors, that means all of your packages have been installed correctly. I'm holding this bar to move up and down while it runs, and then you can keep letting it run. And now you should get a bunch of pop-ups. Note that often your pop-ups will be behind all your windows, so just make sure if you don't see any pop-ups to minimize everything. So, here's the first pop-up. It says input directory of .ms2 or ms2 files and feature tables. Notice now that these also have MZXML files. So I'm going to go into my example files data. I'm going to select that folder. Now, input directory of libraries. So for this, you can just go into Flow, lipid match distribution, lipid match libraries. So that should work well. If there are no groupings, select cancel. So you'll select cancel here if you don't have groupings. Otherwise, take that input file that has groupings. So we do have groupings, so I'm going to select those groupings, and I'm going to press open. Now, retention time window is where your MSMS scans are aligned to your features. So if you have a feature at 6.5 minutes, this would be a 0.3 minute window would be 6.35 to 6.65 minutes. It would look for MSMS scans. The narrower the window, the less false positives, the less chance you get for chiral mixed spectra that don't belong. So sometimes I like to even put this lower, so maybe like 0.18, so plus or minus almost 0.1 minutes, or even 0.1, so plus or minus 0.05 minutes. So it depends on your peak widths, all that. So for this case, I'm going to put 0.18, make it a little narrower to get less false positives. Parts per million is going to depend on your instrument, so you know your mass accuracy when you do your calibration. You can validate it on your file, look for some known things, make sure the MSMS spectra specifically, because this is for MSMS spectra, it is correct within the right tolerance that you set. So for thermo instruments, some high-end QTOFs like 6546, often a 10 ppm window is fine. This is for the precursor ion matching. It's in Daltons now. So it's a window, so 0.01 would be plus or minus 0.005 Daltons. Generally, this is okay for most high-resolution instruments. Again, if your mass accuracy is off, you might want to use a higher resolution. This is the number of MSMS scans needed for confirmation. So if you're doing something where you're not averaging scans and you have a ton of scans across a peak, then you can put more scans here. Let's say 5 scans need to all have those fragments for it to be confirmed, or at least those fragments should be confirmed in 5 scans, I should say, under the peak. Generally, for most QTOF instruments and most thermo instruments, QTOF's average scans, thermo is an average of the oscillation in the Orbitrap, so just 1 scan's enough. Generally, you only get 1 scan, so I press default, which is 1. MSMS intensity threshold, thermo may be 1,000, maybe Agilent's 30, 100. So it really depends where your noise level is. This is very important so you don't get false positives or false negatives if you set it too high, false positives if you set it too low. So we'll select default in this case for 1,000. Now these are important. So this is telling the software where your columns are for your file. So we're going to want to open up that example data again. So let's go back here to our FluoroMatch Modular example data. Look at our CSV file. In this case, row ID is the first column, mass of charge is the second, retention time is the third, and it starts in the second row. So if we look over here at our pop-up box, row ID column / comment column is 1, mass to charge is 2, retention time is 3, third column, and the numeric data starts in row 2. Notice that for this new software, we haven't tested on having multiple headers, so we only tested for a single header. So you probably want a single header, remove all of the extra headers in your output. You can paste them back in at the end when the software is done running. So in this case, probably always have 2. Here, press OK. This is going to be for mass defect filtering, so the default's pretty nice. It's the mass defect for which 95 percentile of the EPA master list falls under. So plus or minus mass defect. So upper limit 0.12, lower limit negative 0.11. So I'm just going to use the default. And then if you look at R, it should be running the code now. Now you should be able to see in your outputs, which is going to be your example data, you'll start to get outputs. Those outputs should generally look the same as what you get in FluoroMatch Flow. So just a brief look over here to see what you should get as the final outputs. This should be your input folder. So in this case, let's just say 1.ms2, 1.csv, and then you'd have your .mzxmls in here too. And your output should look like this with the DDMS2 folder, EICs, fin underscore files, and other. Notice it can take a few hours to run, especially if you have a lot of DDMS2 files, even longer if you have maybe not a high-performing computer. For speed, generally, because it's only the R, it mostly accounts for having multiple cores, which it does use, as well as the speed of each of those processors. So these are your final files and should be generated by the end over here.